right, now we're going to talk about stoichiometry and its relationship to energy. Because as we've learned, stoichiometry is just a series of conversions, and you have to string the right conversions along in order to go from point A to point B. And so if I asked you to convert years to seconds, right, that's going to take multiple steps. If I ask you to go from months to seconds, it's going to take multiple steps, right? But you're going to have a different starting point. And so we have a new conversion factor to work with, right? We've talked about molar mass and how it goes between moles and grams, how balanced equations allow us to go between moles of one material and moles of another material, how if we're dealing with gases typically are measured in volume, and that 1 mole of gas at STP, any mole of gas, is 22.4 liters. We have molarity, which allows us to convert between liters of solution and moles of solute, right? If something is 6 molar, that means there's 6 moles of solute per liter of solution. And if you diluted that down, you could possibly make it only 1 mole of solute per liter of solution. And now we have this new conversion factor right here, right? This new conversion factor relates moles of material to an amount of energy, because a lot of chemical reactions and physical changes have energy changes associated with them. And so while we have all these conversions, right, 18 grams per 1 mole or 22.4 liters per 1 mole, in this case, it's an energy per mole. And so my example here, 1 mole of reactant releases 400 kilojoules of energy when it reacts. And so we can add that energy to our roadmap, right? And so we could start with grams of fuel, right? Perhaps we have so many grams of hydrogen, and we can convert that to an amount of energy, and energy is the ability to do work. And so how many grams of hydrogen would you need in order to do 600 kilojoules of work? And we could figure that out, right? Our starting point can be grams, our starting point can be anything, because there's a relationship between moles and energy. And as long as we can get to moles, we can get to energy. And then sometimes energy is the starting point. And unlike having to go from moles of one thing to moles of another, we can go directly from energy to moles of one thing and then whatever unit we might need. And so let's take a look at hydrogen. We mentioned it earlier. We have a hydrogen fuel cell. It reacts, and we see that it reacts with 10 grams of oxygen gas. And there's plenty of hydrogen gas, so it's not a limiting reactant problem. And the question is, if we use up 10 grams of oxygen gas, how much energy would be released in that process? And so the reaction we're talking about is hydrogen reacting with oxygen to form water. And we would always want, just like stoichiometry deals with, we want to consider the mole ratio, right? But this reaction also has a specific amount of energy associated with it, right? If we go back, we can see that the enthalpy of this reaction is negative 483.6 kilojoules for one of these reactions. So we could have in the denominator 2 moles of water. Instead, we can have in the denominator, we can have 1 mole of oxygen, right? And we could also just as easily have 2 moles of hydrogen. You can define that enthalpy with respect to whatever material in the balance equation you're working with. And so I'm going to go back, right? And we said that 1 mole of oxygen, because that's the coefficient in front of the oxygen, will release negative 483.6 kilojoules as long as there's plenty of hydrogen. And so if we think about this, what we're starting with, right? Our starting place is 10 grams of oxygen, and our ending place is how much energy, right? And so if we think about our starting place, right? it's in the grams. We have 10 grams of oxygen, right? And if we think about our road trip, we are going to an amount of energy. And so that is here. And so that is not a one-step process. We have to go to one conversion, grams to moles, and then we can use the moles to energy equation. So we would take our 10 grams of oxygen, and we have to convert to moles of oxygen. So think about how we do that. And you are correct. We have to divide by the molar mass of oxygen. And oxygen, for every 1 mole of oxygen, because it's a diatomic element, its mass is 32 grams, right? So we've done here is we've converted grams of oxygen into moles of oxygen. And normally at this point, we would go from moles of material to moles of another material, but we don't need to because there is a relationship between moles of oxygen and energy. And what we saw on that balance equation, for every 1 mole of oxygen, right, because the coefficient in that balance equation was a 1, and the enthalpy that was written is negative 483.6 kilojoules. And so now we can see that our moles of oxygen cancel out, and we were left with kilojoules of energy. And so now it's simply putting in our calculator. We're going to do our 10 divided by 32, and then we're going to multiply that by negative 483.6, and we get negative 151, right? We get 3 sig figs. So that's the amount of energy that would be released if we reacted 10 grams of oxygen with plenty of hydrogen, meaning the oxygen is the limiting reactant. Now, in this case, we went from grams to energy, but we can also start with energy, right? Let's say you know that a certain amount of work must be done. You need to move this vehicle from point A to point B, and that takes a certain amount of work, and work energy is the ability to do work. So in this case, if we look at our starting point, we're starting with energy, but what we're going to is liters of hydrogen gas. And so again, it's just a different connection of conversion factors. We are starting with energy, right? And we are going to liters of gas, right? And so if we look at our road trip, we're going to go from energy to moles and then moles to volume. And so whenever we're given a stoichiometry problem, that starting value that is provided is that top box, right? And if you're not into the boxes and you just want to show it as the fractions they are, that's fine too. And we think to ourselves, how do we go from energy to moles? And what we're going to do is we're going to use the enthalpy. And if you recall, again, it was 2 moles of hydrogen plus 1 mole of oxygen goes to 2 moles of water. And the enthalpy that was listed was negative 483.6 kilojoules. So now what I want to do, because this is in reference to hydrogen, my ratio that I'm going to create is going to have hydrogen in the denominator. So I have 2 moles of hydrogen. But I have to ask myself, do I use the conversion factor like this, where kilojoules in the numerator and moles of hydrogen are in the denominator, or do I want to use the reciprocal? And recall that we want to cancel out this kilojoules of energy so we can get to volume of gas. And so that would mean that we would need kilojoules down here, so it cancels appropriately. And so I'm going to put that negative 483.6 kilojoules in the denominator and the 2 moles of hydrogen in the numerator, right? And now I can see that I have successfully canceled out kilojoules. I've successfully gone from energy to moles, right? Because moles is the unit standing. But now we have another conversion because we need to go from moles to volume of a gas. And so you do need to know these conversion factors, right? Volume of a gas, the conversion factor is 1 mole occupies 22.4 liters of any gas at STP. It doesn't matter if it's hydrogen or oxygen, that's always going to be true. Just like 12 eggs is 1 dozen. Doesn't matter if it's a dozen eggs, a dozen bagels. That's a constant. So is molar volume. And so how do we need this set up so that we cancel appropriate and the only unit that doesn't cancel is the liter? We would need the 22.4 liters in the numerator and the 1 mole of hydrogen in the denominator. And now we can check our work. We cancel out units. Yes, they do cancel. The only unit that didn't cancel was the liter. And now we can simplify those values by taking that 2,500, multiplying by 2, multiplying by 22.4, taking that resulting quantity and dividing it by that negative 483.6. And then one thing of note, you can't have a negative volume, and I just forgot to show this as a negative here. The energy is released, and so that's a negative value, and so negative and negative gives you a positive, which makes a lot more sense. And we come up with 232 liters worth of hydrogen gas is required to release that much energy. And I hope you find this helpful, and we will continue to practice this in the days ahead.